Yeah, please go ahead. You can start.
Yeah, hello, can you hear me? Hello?
Yes, yes.
Yeah, okay, and the screen is visible, right?
Yeah.
Okay, so I think I'll go over some of the ideas behind over approximation, what an abstract domain is, and then I'll redo this example with the intervals. Okay, all right. So, like I was saying in the last class, what we want, like what something like ReLUplex does in general, is it keeps track of the entire information in the sense that it will iterate over exact precise assignments for the entire network, right? That assignment, if it can find an assignment that satisfies all the constraints, then we are done. Otherwise, it tries to keep iterating and satisfying a part of the constraints. So for example, in ReLUplex, all the linear constraints are going to be satisfied by the LP iterations, and the fixing of the ReLU constraints is then done, right? And whenever this process finds an actual satisfying assignment, it returns with that assignment. If it cannot find an actual satisfying assignment, it has to actually go over all possible, or at least a large finite set of possible precise assignments before it can rule out the possibility of your property being satisfied, right? So if you have a network that you want to prove to be correct, something like a precise method like ReLUplex will need to potentially go over a large number of assignments. We want to try and avoid that. And the way we can do that is with some over approximation. What we give up is basically we give up precision, in the sense that we end up introducing some situations where we have false negatives. But what we gain is a much more scalable method, which, if successful, can lead us to a proof, right? And I had drawn all of these diagrams showing that, okay, this is the situation where you're going over each one of those assignments. So if you want to show for sure that this black region doesn't intersect the red region, you'll have to go over all of these assignments, right? Whereas on the other hand, you can directly compute some over approximate blue region, and you'll design the representation of a blue region so that it's nice and you can directly check whether it intersects with the red region. If it doesn't, you're done. If it does, then you don't know, right? It could be that the black region actually intersects with the red region, or it could be that the black region doesn't intersect with the red region. It could be that it looks something like this instead, right? So you don't know which of these two situations you have, and then you can't really answer anything conclusive. So Sir had talked about interval domains. I'll give you a little diagram which will work in general for any over approximation situation. With over approximation, you need again two things. You need firstly something that is called an abstract domain, which is going to be, an example would be intervals, right? Which is going to be some way of representing sets of values symbolically, or in the actual memory of the computer. So with intervals, you can represent an interval in the memory as just with two variables, the beginning and the end of the interval, right? You can also have more complicated abstract domains. For example, you can say that, okay, I'm going to keep track of union of two intervals. Then for each such abstract domain, you have four values that you need to keep track of: the beginning and end of the first interval A and B, and the beginning and end of the second interval C and D, right? And once you have these, you can then convert the actual operations in your network into abstract versions of them. So we call these the abstract transformers, right? So, for example, if you have something like, say, you have a situation where you're just taking a variable x and sending it to 2 times x plus 1, right? Now, in the precise world, you will track the precise value of the variable x, and you've tracked the precise value of the output of this operation. So let's say that will be y, and I'm saying y is equal to 2x plus 1, right? And then you model the precise transition involved here. You're saying you're going to say that y is going to be set at 2x plus 1, right? And then whenever you have some assignment for X, let's say some precise assignment like 1, you're going to put some precise assignment for 1, Y like 3. Now, what we want to do is instead, see, X can say if a precondition is going to be some domain, some set of values, X can say take any value in this set. Instead of iterating over all of these, you can, if you could somehow directly represent the set, that would be better, right? So you can say something like, okay, let's directly represent the set of values. We're going to instead of taking one particular value of X, we're going to track a set of values of X. And then this operation, which takes X to 2X plus 1, you can lift that to the set, right? You can say that, okay, we can look at the image of this set under the function which takes X to 2X plus 1. And you're going to have a set of values, right? So now what you know is that any value in your precondition is actually going to be contained in this set. And since this set is the image under this operation that takes X to 2X plus 1, you know that any possible value of Y that you see will be contained over here, right? So any X that you might have gotten due to the precondition is going to be inside this set, and any Y that you might get on the other side, on the output side, is going to be in this set. Then you can check if this image set is actually contained in your post condition or not. If this inclusion holds, you're done. Otherwise, you have a situation where you have to, where you don't know, right? Is this clear? So let's say that somehow we can keep track of sets of values. Then you can set up this precondition set, take its image, and then check for inclusion within the post condition set. Is this okay?
Yes.
Yeah. Now, with an abstract domain, what we do is, see, in general, we can't actually keep track of arbitrary sets of values, right? If I tell you, okay, I have some set of real numbers and I want to represent a set of real numbers in memory and ask you to do that representation, in general, you can't really in any way work with or manipulate an arbitrary set of real numbers in memory, right? Because an arbitrary set of real numbers in general is just an infinite list of real numbers, if you want to put it that way. It's got infinite possible values in it. So you can't, store infinite values in the memory. You can't manipulate them in the memory. You can't do this precisely. What you need to do is instead focus on a smaller representable set of sets, right? So instead of saying that, okay, I'm going to take the exact precondition or which can be potentially an arbitrary set, what we can say is, let's take a bigger set, which is of a nicer form. Say that set looks like an interval, right? Then, in general, my operation 2x plus 1 can take it to, again, some arbitrary set, right? But instead of getting an arbitrary set on the opposite side, we're going to find an interval on the output side, which is large enough to contain this arbitrary set, right? Then we can check whether this interval is now contained inside post or not. And again, if this inclusion holds, remember that pre is contained inside this interval. We have shown that, okay, whatever our operation is, it's going to take this interval to a set that is always going to be inside this interval. And then we can say that, okay, this again is contained inside post. So ultimately, we have proved that P is going to be contained inside post, right? So is this clear? So concretely, in this particular example, what we have is we have a concrete, function or an operation that takes X to Y under F. And instead of dealing with the concrete, instead of dealing with specific values of X and Y, we're instead saying that, okay, this X on this side is going to be contained in this interval. Let's call this I1. And then I'm going to find another interval I2 over here such that image of I1 under F is going to be contained inside I2. Then all I need to do is show that pre is contained inside I1 and that I2 is contained inside post, right? Is this clear?
Yeah.
Okay. So this operation of given an interval, let's say, finding another interval that is going to contain the image under F.
Yeah, so there will be one comment. So the F will be lifted to some F prime, right?
Yeah,
so,
yeah. And that can be sort of captured inside F prime. So essentially we can.
That has to be explicitly constructed.
Yes. So we can essentially find some F prime which behaves like this. It takes an interval I1 and sends it to some interval I2 such that I2 is basically going to be is going to contain the image of I1 under F, right? And then we'll call this F prime an abstract transformer for F. Because what it does is it sort of captures the behavior of F as if it were acting on an interval. It tells us that, okay, if you put F on an interval, whatever you will get is going to be contained in this other interval. So whereas F, our original F was transforming precise values of X to precise values of Y, are now F prime is transforming intervals of values of X to intervals that contain all the possible values of Y. Okay. So in this case, our abstract domain is our intervals, and this abstract transformer is this F prime. Okay, is this clear?
Yes, both.
Yeah.
Yeah, go on. Somebody had a question, I think.
No question, I mean.
Oh, okay, yeah, sure. So in this sort of framework, you can actually set it up for any general representation. You just have to find the abstract transformers for it, right? So I've been talking in terms of intervals, but in general, this I1 can have, still some representable set, but it can be something more complicated than interval. For example, I can say that, okay, intervals are actually not good enough. Let's say that I'm going to take union of two intervals. So I can say that I've got some precondition, and this precondition, all the values of X that I'm interested in, this is actually going to lie in this union of intervals. Then for this sort of a representation of a set where we're taking union of intervals, I can also convert my F to an F prime, right? So I had some precise F that takes precise values of X to precise values of Y. And now over here, I've got a union of two intervals. So I can look for, sorry, I was using blue for the abstract domains. So I've got a union of two intervals. So here again, I can look for some F prime, which will again take this to some union of two intervals, right? And it's again going to satisfy the same property. Now remember that this I1 is now a union of two intervals. So F prime of I1 is going to be another union of two intervals. So, concretely speaking, if I1 can be represented using four things, A, B, C, D, and F prime of I1 is going to give you some, four other things at PQRS. So F prime A, B, C, D is going to give you some tuple PQRS. And we're going to call this F prime an abstract transformer for F if the image of this set AB union CD under F is contained inside this set PQ union RS, right? So again, is this also clear?
Yes.
Yeah. So in general, you can do this, right? In general, you can always, number one, come up with an abstract domain. With an abstract domain.
See, one comment that I want to make is these abstract domains, okay, they are a symbolic representation of infinite sets with finite parameters. Okay, so that is the important thing to I mean, I just want to add because it
Yeah.
just has 4 parameters here. So with those 4 parameters, it is able to capture all the set of elements, I mean, all the elements that are included in that set belong to that abstract domain.
Yeah, yeah. So in fact, for
And
example,
that's why you're able to define the f prime, construct f prime, okay, given any f in code. Okay.
yeah. So for example, over here, when we're talking, say, union of 2 intervals, each of these union of 2 intervals, it's actually infinite set, right? It's a set which contains all of these values here and all of these values here, right? So each set contains infinitely many values. That's the point you're making, sir, right?
Correct,
However,
exactly.
yeah, however, what we need to keep track of, or what we need to represent this infinite set of values is just 4 values, these 4 endpoints, right? A, B, C, and D. So that is the essential idea behind this abstract domain, where you say that you're going to come up with an abstract domain, which means that you're going to come up with a way for representing some nice kinds of sets. So of course, I can't represent any arbitrary set of real numbers with just 4 values, right? You can very easily come up with, counter examples of very complicated sets of real numbers, which I can't represent with just 4 values, right? But I can always represent some nice subset of all the possible set of real numbers. So some nice kinds of sets of precise value, of precise values. These sets itself, they may be potentially infinite. So let's add that. But each representation involves some finitely many parameters. Okay. So this is what your abstract domain is going to be like. And you need another thing, which is that so if you have some system where there are many different, say, concrete transforms or concrete operations that are going on, for each concrete operation in your system.
By the way, this discussion, I mean, that he is illustrating is the subject of, I think it's chapter 5 of that book on verified deep learning. So there is, I mean, it gives a little bit more theory of all this abstract transformers, abstract domains, and so on.
Yeah, and I think there are a lot more examples there. There are examples like zonotopes.
Yeah, you will also show an example. Right?
Yeah, definitely.
It's a little bit abstract.
Yeah. And for each concrete, I just want to lay out this language and then I can refer back to it in the examples. And for each concrete operation in your system, let's say that concrete operation is called F. You will need to come up with some F prime, so that F prime for any one of these abstract set I is going to be some J, where image of I under F is contained in J. Okay. So this is the basic idea. Now, if you can come up with some abstract domain, and if you can come up with some F prime, which is called an abstract transformer, then you can use that to actually try and prove properties on your system, right? And this in general works for any system, not just neural networks. It's very widely used in program analysis. It's called abstract interpretation in that context. And it's definitely also very widely used in neural networks, right? So is this sort of framework clear that we're trying to find an abstract domain and we're trying to find some abstract transformers for that abstract domain and seeing, trying to use that and see what happens with that for your neural network, right? So is this clear?
Yeah.
Okay. So now I'm going to introduce this particular abstract domain, which is called the interval domain. So interval domain is again something that we've already been seeing. Here, each one of our set of values is represented as intervals, right? So our sets are basically just intervals. And this is represented by just two values, right? A and B. So if you were to ask you to, store some representation of an interval in your memory, just need to store the two values, two floating point numbers, right? A and B for the beginning and end of the interval, right? So now I have a question. So if you have, say, a system where you have two variables, right? For example, in the neural network, in a linear layer, you can sort of take a vector consisting of...
Okay, one comment. So the interval AB includes, it is exactly the values that are...
It's included on both sides. So I'm taking this to be the interval.
Yes. Okay.
Right. So it's inclusive on both sides. And that is again something you can play with. Like you can say that, okay, maybe in my interval domain, I want something like inclusive on one side, exclusive on the other, or maybe exclusive on both sides. And you can experiment with that. That will be a slightly different version of the interval abstract domain. And you have to come up with your transforms for that and so on, right? Okay. So now I have, just 1 second, I'll be there. Sorry. So now I have a question for you. So this interval is a set of real values, right? So when I say that, I have a set S and this set is given by the interval AB, this set contains values in R, right? But with a neural network, often if you have a linear layer or something like that, you're dealing with vectors or values in Rn, right? So for example, you might have a linear layer which takes two values or a vector of two real numbers, say a 2D vector, x1, x2, and it might send it to something like a 2D vector which has 2x1 plus 1 and x2 plus 2, right? So can you think of a natural way in which we can use our interval domains, which are designed for values in R, as I have stated them so far at least, and use them to represent, the answer is on the screen, but use them to represent, vectors of values?
Can you repeat?
So intervals can represent only single dimensional values, right? So values that are in R. I'm asking, how can you use intervals to design some abstract domain, that is some representation of a set using only finite many things that can say represent set of pairs of values, a set of 2D points?
A circle or a sphere equation?
Sure, that's one idea, right? So we can say something like maybe, we can say that, we'll have, x comma y, and our interval or our abstract domain is going to then, so what is the abstract domain going to look at? What are the parameters going to be?
Sorry, parameters for what?
For representing the circle. So for example, with the interval, our parameters were a and b, right? So
right,
what is
so
it going to be?
We can center it at, say, a plus b by 2, and like x minus
as in I'm saying
whole square plus x minus y minus a plus b by 2 whole square is equal to some finite radius square.
No, no, okay. Just going back a little bit before that. See, with intervals, what did we have? Each interval is basically a set parameterized by A and B. I of A and B give me the interval A comma B. Here you're saying you were going to do a circle, right?
Right.
So, okay, firstly, what are all the parameters over here?
So we need the center of the circle and the radius.
Right. So let's say the center is some
A
tell
comma,
me
A comma B,
A comma B, and the radius is
C.
C, sure.
Right.
And then the set is given by
all points lying inside x minus A whole square plus
yeah, right.
y minus
Okay.
B whole square
Sure.
to C square, yeah.
Something like this, right?
Yeah.
And yeah, sure. So see, this is an idea, right? Okay, sure. So since you are saying this idea, let me actually use this example. Although I had a different example, but let's use this and let's see where we get with this, right? So, okay, now let's say that my system has got an operation where I'm going to take x comma y to some, let's say 2x plus 1, y plus 2, right? So with intervals, you could have done something. Over here, you need to now somehow take C, A, B, C to some C prime, A prime, B prime, C prime, so that the image of this circle under this transformation is contained inside this circle, right?
Right.
Okay, so maybe you can try as an exercise offline to come up with this, right? But what I want, or rather what I had in mind, is that can we use the intervals themselves as a way to construct a way to talk about sets of 2D things? So there is a way, there is a very direct way in some sense, which is that we can just use a Cartesian product of intervals, right? Which will basically be a box instead of a circle. Right?
Right.
Sure. Okay. So, yeah. So I'm just going to go over this example where we are using intervals and Cartesian products, and then maybe if you want, I can also maybe flesh out this this circle interval domain that you are proposing over here, right?
Yeah, it's fine.
Yeah.
Yeah, I think, this is, yes, you can, this is an interesting idea.
Yeah.
But, but you also have to take into account, I mean, whenever you come up with a new domain, you have to build the corresponding transformers.
Okay? Right.
And the complexity of the abstract transformers, constructing them in such a way that those conditions that Diganta explained in the previous slide, such that the image, whatever that you get, that the abstract transformer returns should be an over approximation of the actual image in circle form in this case. Okay, could be so how but the complexity of building the abstract transformers also has to be kept in mind when you design these domains. But it's an interesting thing.
Yeah. And I think in this,
why don't you, so just flesh out the details for how you would construct it for vectors. Okay.
Right. Yeah. So I'll just flesh out the details of the intervals, and then I think with the circles, it's also fairly easy. I mean, it might be too coarse, but it will be easy to at least come up with something. So, okay, but before we go there, let's just talk about intervals for a second. So let's say that, so I've got 3 examples over here, right? So let's say that my operation is something that takes x to 2x plus 3, right? So let's say that the interval on the left side is -1 and 1. Can you tell me what the interval will be on the other side? And again, all of the answers are on the screen, unfortunately, but still, like, okay, so can you tell me what will it be on the other side, and can you tell me if it is, or justify why it will be that thing? So what I'm saying is key, your values of x and x is contained in this interval -1 and 1, and the operation takes x to 2x plus 3. So then where will this interval -1, 1 go under the operation?
Yeah, for each bound, like the lower bound and the upper bound for x, if you put that in, then we'll get the interval 1,5.
Yeah,
Right.
but I think one small point is kind of left unsaid here. So you want to construct, when you construct the the post, this thing, you want to construct the smallest possible, the tightest interval that contains all the that contains the image.
Yeah.
So that thing is there, because I can always construct minus infinity to plus infinity. Okay. So, I mean, I don't know if you
Yeah, I did not mention that. That is an important.
You did not include it. Therefore, the idea is that it should be an over approximation, and hopefully the tightest possible interval that contains all the elements, of the image. Okay.
Yeah.
So that's when it becomes challenging and interesting. Okay. Because
Right.
otherwise, you could just make it minus infinity to plus infinity to be done with it. Yeah.
Right. So, for example, if I borrow your circle example to illustrate this point that Sir is making, so your say the circle on the input side can look like something like this, right? So let's say this is a circle on the input side. Then the actual function can take this circle to something that is actually not a circle, right? It can take it to something like that looks like this on the output side, right? So this actual function can be some really complicated function taking 2D values to 2D values, and suppose it looks like this. Now, what my abstract transformer should give me, it should give me a circle that contains this, right? So it should give me some circle that contains this thing. But of course, this circle, there are many such possible circles, right? It can give me some huge circle like this, or it can give me this circle, right? Ideally, what the abstract transformer should do, which is what Sir is saying, and oftentimes we can actually guarantee that, is it should give me a circle that is tight. So it is going to contain this and also going to be the smallest circle that is going to be containing this, right? So then the abstract transformer will take this circle to this circle. So it's not only does it contain the image, but it's also the tightest or the smallest possible circle containing the image. Okay, so let's see. So with ReLU, like you said, that you can put these values to 1, like apply the linear equation that I have here to these -1 and 1 to the endpoints and get this thing, right? So we can maybe even generalize this to an actual abstract transformer for this 2x plus 3 operation, which we can write it out like this, right? We can say that, okay, f of this interval, which is the interval between a comma b, is the interval which is 2a plus 3 comma 2b plus 3. This is what you're saying, right, Rohan? I think it was Rohan that answered, right? Hello.
Yeah.
Okay. Hello. It was Rohan that answered.
It was Rohan. Yeah.
Yeah.
Yes. Yeah.
Yeah. Okay. Sure. So, yeah. So we can do this, right? So then, now we have an abstract transformer for this concrete operation that we had previously, right? So now I have another question for you. Is this precise? Are there any values in the image of a comma b under 2x plus 3, which is not, or are there any values in this interval which is not in the image of a comma b under the operation that takes x to 2x plus 3? So, for example, if going again to the circle example, because I think it's very visual. Here there is, for example, this point, right? So this point is not in this image, but it is there in our abstract domain, right? So this point actually represents some imprecision that we're introducing, right? But it might also have happened that, okay, let's say that this f is nice enough, or you just got lucky somehow, that the actual image itself turns out to be a circle. So then the abstract domain is also going to just be, or the abstract image is also just going to be this exact same circle. So then there is no imprecision, right? All the points in the image are precisely the points that are there in your output abstract domain, right? Or the output circle. So I'm asking, is that the situation here? Or is there actually some point in this interval 1, 5? Is there some point x in 1, 5? Which is not in image of -1, 1?
No, it's not possible as it's the, I mean, if you take the derivative, it's positive and it's increasing function.
Sure. Yeah. So you can basically say that, okay, in this case, it will not be possible, right?
Yeah.
Yeah. And then that's a good argument. Like you can basically formalize this argument in terms of using some sort of calculus arguments and say that, okay, this will actually not contain any such point, right? So in this case, what it turns out is that this thing is actually precise. I have a claim, and although you took some calculus arguments, I think you can actually prove this, which is that if you have just a single variable, then any linear transform that you do is going to take an interval to exactly an interval, right? And I think you can generalize your argument to that, because any linear transform on a single variable is either going to be increasing, decreasing, or constant. If it's constant, you're always going to get just that same point. And in the this abstract transform is actually precise. We're not actually losing any information here, right? Does this make sense?
Yeah.
Okay. So now let's go to the next example. So then the next example, the operation is ReLU. So again, for -1, 1, what is the output interval that you would want to have?
And it makes the negatives to 0. I mean,
Right.
-1 to 0 will be 0. I mean, it will map to constant.
Right. So, and what would have happened if, say, my input interval was 2, 3? Where would the abstract transform for ReLU take 2, 3 to?
Same thing, 2, 3. I mean, it's positive. So
it's positive, exactly, right? And again, same question. So again, we can formalize this saying that if a comma b will be f of ReLU of a comma b, right? Because again, we are just going to leave a and b to be the same thing if they're
positive.
Sorry, yeah, not f of this. I mean the interval that is between. Yeah. And if it's negative, we just set it to 0, right? This is exactly what's going on, right?
Yeah.
Yeah. So again, the same question we can ask, is this precise?
Yeah, no point in like 0, 1, right? No point in 0, 1 has any does not have an image in -1, 1. That point doesn't exist.
Right. So there's no point in 0, 1 which does not have a pre-image in -1, 1, right?
Right. Yeah.
It's just fx equal to x for positive part. So that's
exactly
the same thing.
Yeah. So and you said that for 0, 1, but it's true for any like input interval a, b, right? Like if I have any input interval a, b, there is no point in ReLU a, ReLU b, which is not in the inverse image of a, b, right? Is that true?
I mean, yeah.
Yes.
Right. Yeah. Okay. So now we have got 2 examples. Now let's go to the third one, which is, I think, more interesting. So now actually we're dealing with pairs of values. So instead of previously we had just single values, now we're dealing with pairs of values. So 2D points. And the input is again going to be a cross product of 2 intervals. So by that, what I mean precisely is key, x, y is said to be inside I1 cross I2 if and only if x is inside I1 and y is inside I2. Right? This is just the semantic of the Cartesian product, right? So yeah, so now we have -1, 1 to -1, 1. And then if you want to visualize this, this is actually going to look like a box in the 2D plane, right? It's going to be just be -1, 1, -1, 1. So it's going to be some box like this, right? So now my transform takes this thing so takes each 2D point to another 2D point, whose x component is given by x plus y, and the y component is given by x minus y. And now again, I'm asking you the question, what should the output side interval be and why?
I mean, if you take the extreme points, then you can get the -2 plus 2 and -2. I mean, all the four corners of a 2 cross 2, because it's just adding like, yeah, I mean, all possible combinations of the endpoints.
Right. So maybe like, so basically what you're saying is that like x plus y, when we're trying to look at what the bounds of x plus y can be, we'll have to take for the lower bound the possibility that x will be -1 and y will be -1. So we get the bound -2, right?
Right.
Yeah. And similarly for the upper bound, we'll get the possibility that x will be 1 and y will be 1. So we get the upper bound 2, right?
Right. Now you fix any x, and then you can just use the same thing. Like it's again an increasing function. The other part, the y. So then you just vary y over or vary x over, so that you get the rest of the points.
Sorry, come again. Can you just elaborate what you said after?
No, I said once you get the like extreme point, then you just fix one. Say you fix the x variable, and then just vary y. So then you get the other points.
So you're saying fix the x variable and then vary y?
Yeah, I mean for a particular. So for example, x is here from -1 to 1. So if you take anything, say 0, and then you vary y over -1 to 1. So you get the points for like 0. So -1 to 1. You get the. I mean that's what you get the. I mean I'm saying that in the all the points in the this rectangle of -2, 2 cross -2 cross.
No. Firstly, you agree that this is
question, Diganta?
Yeah.
What was your question? What is
yeah. So my question, I think he's probably saying something else. My question was just that why is this an over approximation of the image? That was my question. So for that, you don't need to. I think you're arguing more for something else, right? So can you just say why is this an over approximation of the image? So I'm asking why are all the points in the image contained in this box over here?
I mean, in that case, it's I think just the diagonals and okay.
Okay, so I mean you can argue that very simply. So basically what I'm asking is, if x and y, if x is contained in here and y is contained in here, then x plus y will be contained in this interval, right? That is okay. So I'm saying -1 less than equal to x less than equal to 1, -1 less than equal to y less than equal to 1, right? This implies that x -2 is less than equal to x plus y is less than equal to 2, right? Is this okay? Yeah. That means x plus y is in this interval. Similarly, if -1 less than equal to x less than equal to 1 and -1 less than equal to y less than equal to 1, then we can also say that -2 is less than or equal to x minus y less than equal to 2, right? This is also fine, right? Yeah. So x minus y is also going to be in this interval, right?
Yes.
So that means if x and y is in this set, then x plus y comma x minus y is going to be in this set, right?
Yeah.
Okay. So So I hope everybody agrees that this that this set is actually an over approximation, right, of the image of this set under this operation, right?
Yeah.
Okay. So now I have a question. The question is now, is this precise?
One more question. So, can is it a true over approximation in the sense there's something that is not that is included in the in -2 cross -2 2 that is not in the image?
Yes, exactly. So that is the question that I'm going to ask. Is this precise?
Okay, fine.
Yeah. That is exactly what I'm. So this is the question now. This is the interesting question, which is that, is this precise? Is there any point in this set which is actually not in the image of this set? That is there any point in this set which does not have a pre-image under this operation inside this set, as I think Soham was putting? So any guesses? Anyone wants to answer this? Yeah, I think you should be able to. So is there any point in this set which is not in the image of this box under this 2D linear transformation?
I don't think so.
Yeah, who was that?
Yeah, I don't think so.
So you think that there is no point here which is not inside the image of this 2D box?
No, every point in -1, 1 cross -1, 1 will have a image in the.
Yeah, but that's not the question that Digant asked.
Yeah, no.
Yes, every point we already showed that was an over approximation. The point is the converse of that.
Yeah, there will be points in the bigger set which are not in the pre-image.
Example? Can you give an example?
Like 0, 1.
So you're saying 0, 1.
Yeah.
So 0, 1 is here, right? I can just set x to, I can set y to 0. I can set x to 1. Then 0, 1 is in the image of,
right?
Right.
So maybe 1 point. Oh, okay. Wait, let me think.
Yeah, I think if you think geometrically, this will be easier.
Yeah. See,
draw what is x plus y, draw what is x minus y, and then.
Right. So let's do that, right? So let's do that. But even before that, I'm just going to give you 1 point, and then we're going to also see it geometrically. So the point is going to be, so okay, think about this point, 2, -2. 2, -2 is in this set, right?
Yes.
Right. But can you actually get 2, -2 by taking some xy over here and applying this transformation?
Right. No.
No.
Oh yeah, that will be a rhombus, like a perfect rhombus.
Yes.
On the center. Yeah.
Yeah. And then you're getting a much larger bounding box around it, right? So let's draw that picture, right? So
it's a rhombus, right? I mean, just kind of.
Yeah, it will be a rhombus. Okay, I mean, it will at least be a parallelogram. Not sure if it will be a long rhombus. Yeah, but then you're drawing a box like a rectangle and an axis aligned rectangle around it, right? So what I'm saying is this is your plane, right? And then this is x, this is y. So the transformation takes x. Or takes this, where does it takes x to, right? So it takes 1, 0 to 1, 1. So that means that the x-axis is going to end up along here, right? So it takes this vector to here, right? And then it takes this vector, the vector along the y-axis, to 1, -1, right? So it takes it to here, right? So the transformation is something that takes, sorry, this is y and x. So it's something that takes the x and y axis and sort of flips and rotates them, right? So x-axis goes up to here, y-axis comes down to here, right? So if we imagine our box, if our box previously was going to be this, let's say, this is my box -1, 1, cross -1, 1, right? It will then come down to some box like this. And you're right, it'll be a rhombus, right?
Yeah. I mean,
Yeah, you were right. It'll be a rhombus. So does this picture make sense to everyone? Is this is this an okay visualization? Because see, what's happening is x-axis is going to some axis that is in this sort of an alignment. Y-axis is going to some axis that is in this sort of an alignment. So then if you had a box like this, it's going to end up into being a box like this, right?
yeah.
But remember, our interval or our abstract domain is only going to be some bound on the x values and some bound on the y values. So it's only going to be rectangles where all the sides are parallel to the axis, right? So the abstract domain that we end up getting on the output side is some rectangle that looks like this, right?
Yeah.
So of course, these points are not in your image, but they are in the abstract domain. So in this case, this is actually not precise, right?
Exactly.
Yeah. So, okay. So I have just one question. So just a small question. I want you to think about this. Consider linear operations. So consider linear maps from R2 to R2. And I'm talking about the circle abstract domain that
but before you do that, I
Yeah.
have one other question.
Yeah.
Is this okay? We've shown that this is an over approximation. That is fine. But is this the way that you have derived the tightest one?
yeah,
Tightest one possible in the.
that is a very good question. So does anybody want to answer that?
I mean, sorry, tightest in the sense. I mean,
So in the sense, the
Least.
question is there any smaller box, axis aligned box that still contains our image? So could we have drawn this blue box any smaller? Like, was there any smaller box that also contains the actual image, but it's still an axis aligned rectangle?
no, I don't think so.
No, I don't think so, because the extreme points are being covered in this box.
Correct. Exactly. Yeah. That's the intuition. Yes.
Yeah. And you can also come up with the proof of that, right? Because see, if you're going to say that x plus y is going to be in an interval, then this is the best possible interval you can come up with, right? Because there are, like you said, the extreme points -2 and 2 in this interval are being covered, right? But the combination of extreme points is where things are becoming imprecise. So does that make sense for everyone?
Yeah.
Okay, so I have now like a question. So Rohan, I think it was Rohan, right? So you proposed the circle abstract domain. Let's consider linear transformations from R2 to R2, right? I'll ask you, is it possible to make a precise abstract transformer for the circle abstract domain for linear operations from R2 to R2?
For linear, no.
No, right? Can you just give me some intuition?
From this example only, we had a linear transformation and we made a rhombus, and the over approximation was the square around it. So we can think of a circle as a infinite dimensional polygon. So the over approximation will again be the square.
No, the over approximation will not be a square. No. So when we're in the circle abstract domain, remember the over approximation that we'll get on the other side is also going to be a circle. So in the circle abstract domain, what we would want is, say we have a linear approximation that takes, or sorry, a linear map that takes the axis x and y to something like this, right? So let's say x goes here, y goes here, some rotation or something like that, right? Then what we're going to look for is, okay, where does the circle go? The circle over here is going to go to some circle over here, right? And then our over approximation is going to be the tightest, or some shape over there in general, but our over approximation is going to be the tightest possible circle that you can draw around that shape, right? So here, why were you going to say that you're going to get a box on the other end? So remember, the abstract transform is going to take a circle and give out a circle. In the previous case, our abstract domain were these boxes, right? We were dealing in these boxes. So that's why we were taking these boxes and producing the boxes on the other side. But now, if you're going to design an abstract domain which is going to involve a circle, the abstract transformer should take a circle and give you back another circle, right?
Yeah, right, sir. Yeah.
Right. So then what do you think is the answer to my question? Is it possible to actually make a precise abstract transformer for a circle, for linear maps?
By precise, you mean that but what do you mean by precise? The
right.
smallest? Yeah.
No. I don't mean the smallest. I mean that will an over approximation necessarily come? Like, is there a linear map for which the abstract or that where the circle on the output side has to be an over approximation? So is there some linear map for which the circle on the output side has to be an over approximation? So is there some linear map where, you know, whatever you get on the output side, whatever the circle is that you get on the output side, it has to have some point which does not come from any point inside this circle.
Yeah, like the question that you had, if it's a single variable interval abstraction is precise.
Yeah, it's always precise.
Yeah. So for two-dimensional space, is this precise?
Is this precise, right? So for example, here what we saw, this example, this says that, okay, for two-dimensional space, for linear transformations in two-dimensional space, axis line boxes are not precise, right? Like, no matter what you do in this particular, for this particular linear map that takes, you know, x, y to x plus y, x minus y, you can't come up with a box on the other side that is going to not contain any extra points, right? So I'm saying, can you at least intuitively tell me, is there some linear map for which, in similarly to here, you'll get something on the other side where you can't come up with a circle which will not have any extra points? Right? So no matter what you do, there will always be, you know, some extra point in the circle on the other side.
I cannot think right now.
Yeah, sure. So I'll just give you a linear transform. Okay? So let's say that you have something that is x and y, x comma y, and it goes to, I mean, yeah, it's in general like hard to come up with these things, but let's look at this, right? So let's say it takes x and y to x plus y comma 1, right? So then the picture is going to look like x and y over here. So again, sorry, I have labeled x and y opposite over here. I'm sorry about that. So y and x. So again, the way you will draw this picture is you look at the vector along x-axis and see where that will go, right? So that will go to the x-axis itself. So the x-axis stays where it was. And the y-axis goes to 1, 1. So some diagonal like this, right? So it takes x and y to here. So how will the circle then shift, right? So the circle was previously some perfect circle centered at the origin, although I've not drawn it properly, but let's say that it was some perfect circle that was centered around the origin, right? So now what you'll have is you'll end up having some ellipse that is again going to be centered around the origin, right? Is visually this clear?
Yeah, because x plus y, I mean, that one dimension, like, it's, I mean, expanded.
Yeah, and the axis has been sort of shifted, right?
Yeah, right.
So you have some shear that is going to be applied to the circle. So it's going to look like an ellipse, right?
Yeah.
So then, no matter how you draw, now remember on the other end, what you want is going to be a perfect circle, right? So the actual output of your abstract transformer has to be some perfect circle. It can't be an ellipse. So no matter how you draw your circle, you're always going to have some extra points on these places, which did not come from the original circle that you had. Right? So is it intuitively clear?
Yeah, as a side comment, that's why these kinds of analysis tools that that use this abstract domains, circle is not the domain of choice. Okay, ellipsoid. Okay, they use ellipsoids very frequently used because they are more precise for linear transforms.
Yeah. Because with an ellipsoid, you're actually allowed to output on the other side this precise ellipse. Right? Okay, so is this clear to everyone, at least intuitively?
Yeah.
Okay, sure. So now I'm going to repeat this where, so remember what we've already done, what we sort of established via these examples is we already have abstract transformers for the interval domain. We have abstract transformers for linear maps and for ReLU, right?
Yeah.
So now I'm going to use that to sort of propagate these abstract regions across a neural network and see what interval we get for each point, right? So let's go through that. Sorry. Right. So again, for this network, the intervals on the input side is just -1, 1. Okay. So now tell me, what will the interval for x3 be? Remember that what we have is that x3 is equal to x1 plus x2, right? This is 1, so it's 1 times x1. And this is also 1, so it's 1 times x2. So x3 is equal to x1 plus x2.
Diganta, didn't we do this last time?
Yeah, we did do it. Do you not want to go over this, or I thought that, like, since I did it in a hurry, I'll maybe go over this. But if it's okay with you, I can skip.
I think it's clear.
Okay, sure. All right. So can you tell me, the last time the interval that we got is 0, 4, and I think I asked people to check if this is precise. Can you tell me, was this a precise interval? Is there actually some value of x7 that is in 0, 4, but that the network can't achieve?
No.
Are you sure? There is. Let's think about the value x7 equal to 4, right? So let's say x7 is equal to 4. What is the only, the way that can happen is this plus this should be equal to 4. Right? Now, if this plus this should be equal to 4, then, so remember that this guy is x1 plus x2, and then this guy is x1 minus x2, right?
I got it. The max value will be 3.
Yeah, exactly. The maximum possible value will be 3, and we'll prove this using some different abstract domain later on. So is it clear to everyone else, or does everyone?
X6 can have the max value as 1, and X5 can have the max value as 2, and therefore we can only have X7 as 3.
Right. But then why did our interval domain give us 4? Where exactly in the interval domain did we end up introducing an imprecision?
For the
See,
value of
x6,
x4.
huh?
For the value of x4.
See, but x6, so you say that x6 can have the max value of 1. The x6 can have a max value of
No. Like for x4, if x1 and x2 are both 1, then it goes 0. Oh, okay.
No, but it can happen that x1 is 1 and x2 is -1. So x4 is 2.
Right. So the interval for both x5 and x6 is right, 0, 2. But not like the whole interval is not possible for concurrent values of x1 and x2.
Exactly, right? So it can't be that x5 and x6 are both have a value of 2, right? So the only way x7 can be 4 is if x5 and x6 both have a value of 2, right? Because maximum value of x5 is 2, maximum value of x6 is 2. But for x5 and x6 both to have 2, x3 and x4 both should be 2, right? And then notice that this is exactly the same example that we were seeing before, correct? What is this layer doing? It's taking x comma y to x plus y comma x minus y, right?
Right.
And what do we have? We had -1, 1 cross -1, 1 on this side, and this on the other side we're getting -2, 2 cross -2, 2, right? So again, we are asking whether 2, 2 is possible as a value or not, right? Is whether 2, 2 is within the image of this operation or not, right?
Yeah.
And of course it's not, right? So it's basically the same situation that was happening before.
Yes.
Right. So maybe let me just copy this to the next slide just for clarity. Yeah. Right. So is it clear to everyone else also?
Yeah.
Okay. Right. So the only way that can happen is if these two are 4, and then these two being 4 means x3 and x4 being 4. And again, you have the same situation where you're looking at one of the, your blue square is this, and your actual image is this sort of a rhombus. And then again, you're looking at this particular point, right? So, yeah, so this interval domain is actually not sufficient, right? There should, or at least for this particular network. Hello.
And for depending on the property that you want to verify, if your property is also a very weak property, then it might be sufficient.
Yes.
So,
yeah, definitely.
It's not definitely not sufficiently precise for the precise reason it doesn't capture these kind of relational dependencies. Okay.
Yeah.
Across, among different variables.
Yeah. So basically what I want to say is that for this particular network, the property that we wanted to prove was, if you remember, is that x7 is less than equal to 3. This was our property. Okay. And for this property, the interval domain is not good. We need some better abstract domain. Okay. All right. So, sorry, what's the time? How much time do we have?
It's 15. I think this is a nice place to stop, I feel.
Yeah. I'll maybe take like half an hour.
And I think you should kind of summarize what more you plan to do with DeepPoly, and maybe let's think of you have to give instructions, so that can be done offline. Instructions how to download DeepPoly and so on and so forth that we can upload, and can also make some examples that they can do. With like we said, for ReluPlex and everything, we have to make some class exercise. That's exercise on us. So give a summary of what more do you plan to discuss on DeepPoly next class. Just a teaser, yes.
Right. So basically, I'll just show you the next slide that I have. I'm going to describe what the precise abstract domain that DeepPoly uses is. So DeepPoly, what they do is they have designed a abstract domain that actually is smarter than intervals. Intervals is very naive in some sense. It's the first thing that comes to mind when it comes to abstract domain, right? Deep Poly has their own abstract domain, which is somewhat smarter, and it's good enough for this particular property. I'm going to describe what the abstract domain is. I'm going to walk you through this example using that abstract domain. And I'm also going to, that will involve a few slides. And then I'm also going to talk a little bit about, so if you were to extend to other networks beyond ReLU, what you might need to do. And then that will basically help us segue into these other paper, which is called LinSim. So
yeah, like for other kinds of activation functions.
Yeah, for other kind of activation functions, exactly. Yeah. Right. So I'm going to basically describe the deep poly abstract domain and the abstract transformer for linear and ReLU, and go over this example in some detail with that. Okay.
Okay.
Thank you.
All right. Thank you, everyone.
Thank you.